Hey guys, Mrs. Ellis here, and today we're going to be talking about counting significant figures. What are significant figures, you may wonder? These are going to be certain digits and the estimated digit of a measurement. Together, they are collectively called significant digits or significant figures of the measurement. There are rules that must be followed when we count significant figures and when we complete mathematical calculations with measured values. The first rule that we're going to look at is all non-zero numbers are significant. So you might ask, what is a non-zero number? Well, I'm sure that you could figure that out. Our non-zero numbers are 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of those numbers are going to be classified as significant. For example, here we have a measurement of 23 grams. 2 is not 0, 3 is not 0, so here we have two significant figures. Let's look at another example. We have a measurement here of 63.76 kilograms. 6 is not 0, 3 is not 0, 7 is not 0, and 6 is not 0. So here we have four significant figures. The next rule that we have is that embedded zeros are always significant. These are also known as trapped zeros. These are going to be zeros between non-zero numbers. Well, zeros that are between non-zero numbers. For example, here we have 108 milliliters. This measurement has a 1 that is not 0, an 8 that is not 0. According to our first rule, these are both significant because they are not 0. But what we notice is we have this 0 here in between our 1 and our 8. Numbers are trapped, they're embedded, they're sandwiched, and they are significant. So here we have three significant figures. Our next example is 1,008 milliliters. 1 is a non-zero number, so that 1 is significant. 8 is a non-zero number, so it is also significant. And what we find is here we have 1, 2, 3, 4, 5 zeros that are trapped or embedded in between the 1 and the 8, which is going to result in 7 significant figures in this measured value. The next rule is that leading zeros are never, ever, ever, ever significant. Picture the leader of a race. The leader of a race is going to be in the front. The same thing with leading zeros. They are going to be zeros that come before the first non-zero digit. Okay, these are simply placeholders. What we see here is a measurement of 0.123 kilometers. This 0 is before the first non-zero digit, so it is not significant. It is a leading zero, and leading zeros are never, ever, ever significant. So we look, the 1, the 2, and the 3 are all non-zero numbers. Here we have three significant figures. Our next rule says that leading zeros are never significant. I'm sorry, this is the same rule that we just did. This is just another example. They're never, ever, ever significant. And what we see here is that we have leading zeros that are holding the place of the 7 in our measurement 0.0007 meters. These zeros are leading zeros, and leading zeros are never significant. So here we have the 7, it's a non-zero number, so we have one significant figure. Now we're on to our next rule. I apologize. Let's say you're in that race and you're trailing behind. Okay, the same idea here is when you're trailing behind in a race, you're towards the end. Trailing zeros are going to be after the last non-zero digit. Okay, so trailing zeros come after the last non-zero digit, and these are significant in some different situations. Trailing zeros are significant if there's a decimal point present in the number. It doesn't matter where that decimal point is. If we have a trailing zero that comes after the last non-zero digit and there is simply a decimal point in the number, the trailing zeros are significant. We also have the option for a line to be over a zero. That will create significance in the zero. So for example, here we have a measurement of 200 grams. we have 2, which is a non-zero digit. It's automatically significant. But here, these zeros are trailing zeros. And there's no decimal point. And there's no line, which means these zeros are not significant. In this number, we have 1 sig fig, and that's the 2. In our next example, though, we do have a line present over the first 0. If there's a line over a 0, that trailing 0 is significant. So we have 2, it's not 0, so it's automatically significant. The first 0 has a line over it, so it's significant. And then the last 0 is a trailing 0, and there's no line present over the top of it, and there's no decimal point in the number, so here we have 2 significant figures. In our next example, we also have the same measurement, 200 grams, but there's a different precision. So what we notice is that 0 with a line over it has changed, and it is now the last 0. Well, when this 0 becomes significant, because there's a line over it, that traps this 0 here, the first 0, between the 0 with a line over it and the non-zero digit, the 2, which means that the trapped 0 is significant, and the 0 with a line over it is significant, which results in 3 significant figures. All right, so here's another example. Trailing zeros are significant only if there's a decimal point present in the number or if there's a line over the 0. Here our measurement is 10,800.00 grams. Well, what we see is that there is a decimal point present in the number. All of these zeros are considered trailing zeros because they come after the last non-zero number, the 8. Because there's a decimal point, all the trailing zeros are significant, okay? So 1 is significant because it's not 0. This first 0 here is significant because it's trapped between the 1 and the 8. The 8 is significant because it's not 0. And then all of these trailing zeros are significant because there is a decimal point present in our number. So that's 1, 2, 3, 4, 5, 6, 7 sig figs. All right, here's our last example for this rule. It says trailing zeros are significant if there's a decimal point present or a line over the 0. Well, what we notice here is 1 is significant because it's not 0. The first 0 is trapped. 8 is not 0, so it's significant. And then these here are trailing zeros. There is no decimal point, and there's no line over any of those zeros, so these are not significant. Which means that we're going to have a total of 3 sig figs. That's going to be the 1, the 0, between the 1 and the 8, and the 8 itself. Here's another rule. It says zeros following a decimal point in scientific notation are significant. The basic thing that I want you guys to walk away with is understanding the number of significant figures must be the same as you go between scientific notation and standard notation. So here we have numbers that are not in scientific notation. This is 1,500,000. This has 2 significant figures. When we convert this to scientific notation, we're simply going to move the decimal to the left until it is simply after the first number that is not 0. 1, 2, 3, 4, 5, 6 times is how many times we're going to move that decimal to the left. Our scientific notation is going to be 1.5 times 10 to the 6th milliliters. This 6 is positive because our original number was greater than 1. For the next example, we have 1362, and this trailing 0 is significant because there is a decimal point in the number. This has 5 significant figures. So when we go to scientific notation, that decimal is going to move to the right now in this case until it is just after the first non-zero digit. So it would have to move 1, 2, 3, 4 times. Our number here is going to be 1.3620 times 10. 1, 2, 3, 4 times 10 to the negative 4th grams. This 4 is negative because our original number was less than 1. But what we should see is that we're maintaining the same number of significant figures as we move from standard notation, which is what we have here, to scientific notation, which is what we have here. So here we have 5 sig figs, 1, 2, 3, 4, 5 sig figs. Here we have 2 sig figs, and here we have 2 sig figs. We'll look at how we go back and forth between those a little in more detail later. The next rule we're going to look at is when exact numbers appear in a calculation, they do not impact the number of significant digits because they are infinitely significant. This would include counted values. Like if we counted that there are 23 people in our class, there's never a partial person. So this would be like saying there's 23.000000 people, and that would be a value that's infinitely significant. Okay, so that's never going to impact the number of significant figures in a final answer when we're doing a calculation. We also have conversion factors or equivalencies. So here we have an equivalency that there are 60 minutes in 1 hour. You could use that in a mathematical equation as 60 minutes per hour, or that there's 1 hour for every 60 minutes that pass. This is considered to be an equivalency, and it is infinitely significant, so it will never impact the number of significant figures in the final answer when doing mathematical problem.